I'll leave my windows down. All right. Now you can turn on the projector, though we don't need it quite yet. So let's just quickly go over, if I don't do anything very quickly, but the issues of safety, okay? 3 areas that we always have to keep in the back of our minds. Can you think of what one might be? Second? Oh, yeah, out of the exit. Okay. Now, that does fall into what we're talking about. There are 3 things that we have to worry about. Well, you don't have to worry, but just have to think about it. One, let's take, if you're exiting the building, the reason to do that is what if there's a fire in the building? So let's take worst case scenario right now. Say my computer blows up, okay? Let's hope it doesn't. But what if it did and the fire started in this room? It blows up and starts the papers on fire, my books on fire, and that kind of stuff. What do we do? Exit is one thing. Before we do that, what? Okay, excellent. Okay. Actually, a better number than 911 would be your campus police number. Now, most of the doors that I've come into this building have a piece of paper, 8.5 by 11, giving the Birmingham and the Bessemer campus police number. Now, that's not the lieutenant's office number. That is the phone that some duty officer has on his or her belt. They've got it on them at all times. Someone has it on them at all times. So that's a great number to have as a speed dial in your phone, if you got a phone like that. My phone's out of my office. I don't ever bring it to class, so I don't want to ring in my phone in class. So if you got a phone with you, that. Otherwise, 911. Okay? So that's one good thing to do. But also, before we leave the building, we can make sure that everybody knows there's a fire in the building. And how do we do that? For a fire alarm. Now, where's the closest fire alarm? You don't know. Probably nobody knows, okay? This is a diagram of the second floor of the building. Actually, it's not quite correct because this is actually first floor down here, but that's okay. Back when this was done, they didn't have this part in here done anyway, okay? But all the part you see here that is contiguous, okay, this is the old part of the building before fire alarms were part of the code. So there's not a fire alarm in sight anywhere on any of these halls. But there's not one too far away. If you go out the door here, hang a left, go down that little half flight of stairs just right over there, and then go down to that little corridor there, just past the restrooms, go through that, then you're entering the new part of the building, the newest part of the building, and there, if you turn either left or right, you'll see a fire alarm both places. So that's where you go to pull the fire alarm. Okay? Now, the fire is burning in here. Do we just let it burn? With something. What would we use? Okay, where's the closest fire extinguisher? Okay? Pretty observant, aren't you? Right here, 5 feet from where I'm standing, this fire extinguisher, right there, in a box, right there. And I know you've always want to break that glass up. So you get to break the glass if that happens. Now, hopefully that won't happen. Okay? But then, after that, we get out of the building, especially if we have more people than just you and me. Okay? And where we go from here is, again, go out the door, hang a left, go down that half flight of stairs, and immediately at the bottom of the stairs, now if you went to do the fire alarm, okay, then when you come back this way, go down that half flight of stairs, a full flight of stairs here, then go out of the building, straight away from the building. Here you are, coming out of this door right here, go down to the parking lot you see right down there. And now I'll be coming after I finish trying to put out the fire or whatever. And then we will be good. Now, if we hear the fire alarm, it's not in this room, then we just proceed out of the building in that way. Now, I will be the last one out, okay, because you're faster than I am.
But I will be the last one out in case one of the other people here has a bad leg or an ankle or something. I'm going to be sure that the slowest person gets out. But when I get down there, I'm going to take the roll sheet and I'm going to call roll. I have to account for everybody. If you have wandered off somewhere, then I have to go back in looking for you in the burning building. I don't want to do that. Okay, so stay together as a group until we've called roll and we've heard from them. All clear, you can go back in. Hey, no more classes today, or we're going to distribute to other buildings. They'll tell us something, but we'll wait and get that done. Okay? And then we'll go from there. All right, any questions? That would be fire, chemical spill, anything like this that we need to get out. We don't hang around near the building because if there is a fire, there could be an explosion. Glass could get thrown out. That's why we go all the way down to the parking lot and gather down there. Not to get in cars, but together. Okay, another kind of emergency. If not fire, what else could be a safety issue? Weather, exactly. If we hear that alarm go off, and you can hear it really well here. The alarm is somewhere, the siren is somewhere pretty close to here, so you can hear it pretty well. If we hear it, what do? Say that again.
Well, if it's a tornado, then like you get up against the wall or something.
Okay, that is a good idea, but here are the two things to keep in mind. You go low and interior. So the wall idea is good because that's where the greatest strength is, but not this wall because there's glass here, okay? Not even out there because a tree could fall across the building and come through and damage there. We go low and interior, okay? So what do we do then? We go out the door here, hang a left, go down that little half flight of stairs, hang another left, go down one more flight, and rather than going out, we go in. Okay, now the first floor down there is a lot like the second floor here. Okay, when you come down that stairwell, you'll see restrooms right in front of them. They are interior. Okay, not a bad place to be because the walls are close together. There are lots of corners. There's a lot of strength there. Okay, and this back wall here, when you're down on the first floor, the back wall here is backed up by solid soil. There's the building above it, but no crawl space, nothing. It's solid. That is a good wall to be against. When you set a bit against the wall, down on the first floor, the back wall there. Okay? But, especially if it is a really severe weather emergency, there's a good chance that the power will go out. And if the power goes out, the restrooms have no emergency lighting. So you're stuck in a black restroom for how many hours? That may not be your favorite place to be. So there's actually one or two little steps further down until you get underneath this corridor is the dean's office. Now, most of the time she's not over here. I happened to see her here this morning. So occasionally she might be here, and if she is and invites you in, that's a good safe place because that back wall is backed up by soil. It's a good, solid place to be. And the walls are close together. Okay, so that's pretty safe. The next room down is a classroom. Now, it's probably about this size, so the middle of the room probably isn't the best thing, like you said, against the wall. Back wall is the best. Corners are even better, okay? But all that is pretty safe, okay? Then there's glass doors in the hallway here. When you go through the glass doors, you're into the library. Just inside to your right, there's a computer room that's smaller than the classroom. That back wall is very good, and the corners and the walls are good. Okay. Right next to that is what I call the reference room. That's where the atlases are, the books you don't usually check out, but just use as a reference. That's not a bad place to be. That back wall is pretty safe, but there's bookshelves there and books and things. And I guess the building really started rocking and rolling. Some things may fall, but usually that wouldn't happen on the lowest level. But don't go any further in the library because then you're on an exterior space and there's windows. So don't go any further than that reference room. Actually, the one place I've left out may wind up being most people's choice to be, and that thing that's a little negative about the hallway, there's no corners. It's straight, okay? Second thing is it doesn't have that back wall that's solid, okay? Nothing behind it, the soil, okay? But it is a good, strong wall, and the advantage of the hallway is emergency lighting on both ends. All these others are, if the power goes off, you're in the dark. If the power goes off in the hallway, at least you have a little bit of emergency lighting. And that's where most people, I think, would hang out, leaning against the wall, sitting down, chatting, whatever. We stay there until we hear all clear. Okay. So that's for a weather emergency. Down in interior. Okay? Away from rooms with windows, exterior rooms. All right, now the third safety, and also I will be the last one out. I'll carry my roll sheet. If I go down there and can't find the class, right now you're the class, okay, then I have to go back looking for you and putting myself or the fire people or whoever it is in danger. So please don't do that. Okay. And then once we have called roll, you can mingle among friends if you want to. But do not say, oh, I left the dog outside, I better go home and get it. No, don't worry about the dog. Dogs will take care of themselves. The worst place to be in a weather emergency is on the road. Tornadoes pick up cars and throw them around, okay? You don't want to be in a car. They say if you're on the road, pull over, get in the ditch, because you don't want to be flat level ground. Okay. Now, the third one is one I never even used to think about. And what is it? Active shooter. Now, I'm hard of hearing, okay? So you'll probably hear if there is a pop, pop, pop before I will, or rat-a-tat-tat, or whatever it is, and it sounds like gunfire, stop me and say, that sounds like gunfire. What do we do then? Okay, I do have a key for this door. And the reason a key is necessary, there's nothing you can do to lock the door from inside. Not even if you open it, there's no button you can push to lock it. I have to physically go outside and lock the door from the outside, then don't close it. I need to get back in. Okay, I'll come back in and close it. Turn off the lights, turn off projectors. One thing you do, as soon as you hear that, while I'm locking the door, you got a cell phone? Okay, that's when you dial. Campus police is the best. After that, 911. Or if you don't have campus police, dial 911. Okay? As soon as you do that, turn the cell phone off. We do not want the ringtone coming on right when he's walking down the hall. Okay? Usually it's a he. I've only heard of one time it was a female mass shooter. So we don't want that to happen. Okay? So turn the cell phones off. Okay? Now, I lock that door for what good that is, and it will be good. But this door is open. This door is open. That door is unlocked. And the next one is unlocked. I don't have a key for that next classroom. Okay? Now, sort of a good thing, most of the time, they've been forgetting to unlock that door. I think today they unlocked it. So you can never tell. But what I would do is go in there and at least close that door. If it's locked, then he can't get in. Okay? If it's not, I turn off the lights. And this door does have a button here you can lock. Don't do that because it locks from the inside, but you can still get in from the outside. That's where he's going to be. So don't lock this one. This one has a deadbolt, but I don't have a key to it. This one, however, has a button, just like that one did. This time it locks from the outside, not from the inside. So we can get out, he can't get in. So this is the one I would be locking. I'll close that door, it's closed. Lock this door, it's not locked now, it will be. Close this door. Why? Doesn't have a window in it. He might be able to look through and see somebody. So close this door. We don't want to look. Look, it seems like it's totally deserted. Now we leave this one unlocked, and we'll close that one too. And then I've already locked that one. We get right back there. Okay? Why? Or anywhere back there. because he can fire through the window. He can probably break the window and do some maneuvering. He can fire through this probably reasonably effectively, maybe even the door. I don't know if this is a solid door or it's just I think it is. Okay? So that would be a little more difficult. But concrete block, that's kind of tough. If he were trying to shoot through that, he's going to have more stuff firing back at him than is going to come through to us. So that's where we are. We stay there, quiet as a church mouse, until we get the word. Definitely get the word from someone in authority that it's all clear. Okay? So that's what we have to keep in mind. Now, if somehow, and it's quite possible, that the guy could come in that other door, break the glass in the other one, reach in and unlock and open the door from inside, come through the next door, and then come through. If he does, don't be a hero. Your future's ahead of you. Mine's mostly back here. Okay, so let me deal with him. Don't you're too valuable, so don't do anything. Hopefully, it'll never come to that. I really hope it won't. I was in the military, so I've had a little bit of training, not on active shooters, but I can manage to wing it, I think. Okay, so all right. Any questions on safety of any form whatsoever? Now, one reason I did that is so anyone else coming into class, I don't have to repeat that again. I've recorded it. I'll tell them to go to the second class and you'll hear it. Okay, so I think we're finally ready to start with linear algebra. Okay? Now, we didn't get started anywhere last time, did we? Okay. And you said you've already had the first part of linear algebra. So this should go pretty quickly. Sorry, you folks who aren't here. If you had been here, we'd slow down to whatever speed you wanted to be, but we're just going to go. Now, 1.1, or Chapter 1, is systems of linear equations, okay? And you're probably pretty familiar with that, okay? 1.1 is introduction to systems of linear equations, and just to get the nomenclature right, what if you had this as an equation? Let me get my pen set up. Okay. AX, or let's see, they do A1X plus A2Y is equal to B. Okay? Now in this, the A's, A1 and A2, are both constants, numbers, just scalar quantities. B is a number, scalar quantity. X and Y are your variables. Okay? That's a linear equation. What makes it linear? Second? First power. You do not have any power of any variable other than 1. Okay? Well, this you could say is X is 0. Yeah, okay, 0 or 1. No fractional, no decimal, no multiple, anything greater than 1. Okay? Nothing except a 1 for your coefficients, your exponents of your variables. Okay? Now, this is a linear equation in 2 variables. No way you're going to be able to solve that exclusively. Okay? Because given any x here, there could be a y. If you give a different x, you could have a different y. So there's an infinite number of solutions for that equation. Okay? So, just to let you know, they're not talking about that yet, but I'm just talking about it. Okay? Now this is also, since there's 2 variables, x and y, we assume this is a planar equation, you might say. This describes a line in a plane. Linear equation, this graph would be a line in a plane. Okay? Now, if you had 3 variables, a1x plus a2y plus a3z, I can't write, is equal to b. So keep that the same. Now all 3 a's are constants and your b's are constant again. The x, y, and z are variables. Now you have a linear equation in 3 variables. No way you can solve that by itself because you've got 3 variables with only 1 equation. So that's going to be a parametric type of a solution. Okay, but we're not getting into that now. All right, That describes something in space, 3 space, okay? Now, especially in linear algebra, we can go up to n space. I can't visualize n space. I can't do anything beyond 3 because I live in 3 space. I can visualize 2 space because that's pretty easy. Now, what's hard is drawing 3 space on a plane. That's hard to do, and you'll see my graphing is awful, okay? But that's a linear equation in 3 variables, x, y, and z. So, in general, here's your, because you don't have a book yet, do you? Here's a definition of linear equation. Now, did I talk some about the book when we were doing the syllabus? Okay. And I may have mentioned Ron Larson was the author, right? Okay. What's that? Yeah. Did I tell you what stuff it was that bothered me?
No, he said he was going to get to it.
Okay. Here's what it is. I've taught 5 classes besides this one using text with him as an author. Pre-calculus for algebra and trig used 1 text, and Cal 1, 2, and 3 used another text. So 2 texts before I did this one. In both of those other texts, when he was referencing a vector, he put it in angle brackets and put so one more. Sorry. Poor people listening at home, they didn't know that was coming. Okay. That's how his convention was, which is sort of standard for listing a vector. In parentheses, that would represent a point. Okay? 7, 3 in parentheses would be a point on the plane. 7 on x, 3 on y. Okay? 7, 4, 7 would be 7 on x, 4 on y, 7 on z. That would be out there somewhere. Okay? If it's in parentheses. If it's in a vector, that would be a vector whose initial point is the origin and the terminal point would be that point. Okay, that would be a vector. Then you put it in angle brackets. That's how he did it in the pre-calculus text and the calculus text. In this text that we use vectors all the time, he puts them in parentheses. And it sort of drives me nuts because you just look at it, you have to go from context whether he's talking about a point or a vector. Why does he use angle brackets? I don't know. That was the thing that bugged me about this text. Otherwise, it's a perfectly good text. But since you don't have it, let me write down this definition of a linear equation in n variables. We're not going to limit ourselves to how many. Okay? A linear equation, I'm going to abbreviate like crazy, linear equation in n variables. Okay? I'll abbreviate like crazy. X sub 1, x sub 2, x sub 3, ... all the way up to x sub n. For some reason, I started writing in A. I don't know where that came from. Okay, x sub n. I'm sorry. The sneezes loosened everything up. Okay? Has the form, okay, a sub 1, x sub 1, plus a sub 2, x sub 2, plus a sub 3, x sub 3, plus ... all the way up to and including a sub n, x sub n. Okay? And that's equal to some other constant, b. Just like we showed before with 1, 2, and 3 variables, this is within variables. And again, the key is every variable. Now, these are your variables. The a's are your constants. Okay? Before they were doing x, y, z, but now you got n of them, so there's not enough letters in the alphabet, so we call them x sub 1, x sub 2, x sub 3, x sub 4. Because no y sub 1, y sub 2, yeah, or whatever, but whatever you do. You just don't usually do x, y, z, a, b, c, just too many letters to account for, especially since you're already using A's for constants. So x of 1, x of 2. Okay. Those are the variables. A's and B are the constants. Okay. So that's how we represent it. Notice none of the variables has any power other than 1. Okay. All right. The coefficients a sub 1, a sub 2, a sub 3, all the way up to and including a sub n are real numbers. Okay? Now, a lot of times they're integers, okay? Most of the time we're going to play around with integers, but they could be any real number. They could be fractions, decimals, rational, irrational. We don't put any complex numbers in there, but they could be any real number, okay? And the constant term, that's your B, is also a real number. Okay? Again, positive, negative, fraction, decimal, rational, irrational, it doesn't matter. Okay. The number a sub 1, a sub 1 is called the leading coefficient. Okay? And the x sub 1 is called the leading variable. Now, if we were strictly dealing with equations, 2 or 3 equations, 2 or 3 unknowns, stuff like that, it really doesn't matter which order you do things. You just have to do them the same for all of them. But when you get a n-degree polynomial, a linear equation, it is a type of polynomial, but it's a linear equation, designate whatever the first one is. Because what we're going to be doing when we get into matrices, we're going to be referring to the leading term. Leading term. So that's why we make special thing, leading coefficient, leading variable. Okay? Because we will do a lot with that leading term. Okay. Now, what linear equations have, even though you have a number multiplied by a variable, you never have a variable multiplied by a variable. You can't have an x2 times x7. No. Every term has a single, it's either going to be a constant or a single variable in it. It can be multiplied by numbers, but it can't be multiplied by a different variable. Okay, so they do make that. So, let's look at a few. All right, to erase. This is all really simple stuff now, but the nomenclature is what we're after. 3x plus 2y is equal to 7. Okay? Is that linear or not non-linear? Linear, of course. How about this one? 1/2 x plus y minus pi z is equal to root 2. Linear or non-linear? Linear. The variables are all to the first power. Okay? It doesn't matter if a coefficient's a fraction, positive, negative, irrational. It doesn't matter. Those are just numbers. Okay? It's the variables that make the difference. How about this? Strange one. Sine pi x1, minus 4x2 is equal to e squared. Linear or nonlinear? Second? It's still linear. Your variables are x1 and x2. They have no exponents. They're linear. E has an exponent, but guess what? E is a number. It's not a variable. Okay? E is that number 2.7, blah, 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 blah. Yeah. It's a number. Okay? It's also a function, but it's a number. Okay? Sine pi, sine x3, that would not be a linear thing, because now you're taking a linear term, a linear variable, but operating on it with a nonlinear function. That would not be. But sine pi, pi is a number, sine pi is a number. So that doesn't bother, okay? It's the x1, it's the variables. That's where you focus. How about this one? xy plus z is equal to 2. Linear or nonlinear? Nonlinear, because here you've multiplied two variables together. Can't do it. How about e to the x minus 2y is equal to 4? Nonlinear, because your x is not it's your variable here, but it's raised to an exponent of a number. So that's a function. That's not a linear function either. It's definitely nonlinear. Okay? Sine of x1 plus 2x2 minus 3x3 is equal to 0. Linear or nonlinear? It's nonlinear, because that first term, even though the x is only to the first power, you're operating on it with a function which is a nonlinear function. So no, that's no longer linear. So it's not just that the x, y's, and z's have to have exponent 1. They can't be operated on by a nonlinear function. It must be incorporated in a linear function. Okay. Now, some more nomenclature. If you have an equation, any of these equations, a solution, I'm going to abbreviate this, that's my thing I'm dividing, a solution of a linear equation in n variables, okay, in n variables, is a sequence of n real numbers S1, S2, S3, comma, dot, 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 up to and including S sub n, that are arranged to satisfy, this is a difficult sentence, the equation when you substitute the values in. That's a really difficult sentence. Okay. All right. And here's what they are. x1 equal s1, x2 equal x3, s equal s2, x3 equal s3, comma, dot, 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 all the way up to and including x sub n equal s sub n. Okay. So, this equation is going to have a solution. I'll see if I can do it. For instance, 1, 2. That would be a solution, right? Because 1 for x makes that 3 times 1 is 3, 2 for y would be 2 times 2 is 4, 3 plus 4 is 7. 1, 2 would be a solution set for that equation. I mean, a value, a solution value. It's we call it an ordered pair that works for this. What they call it here is a sequence of n real numbers. 2 variables, 2 real numbers. Okay? Is that the only one? No. 0, 3.5. There would be another thing, because 0 here, 3.5 times 2 is 7. Or 2.5, 0. Okay? Or you can go on and on and on. There's an infinite number of ordered pairs that will satisfy that equation. Now, I'm not going to make up some that will satisfy this one, but there is ordered triplets. Plug in something for this. I'll give 2 root 2, 0, 0. There's one. Okay. 0, root 2, 0. There's another one. I'm not going to make up one. I could. 0, 0, negative root 2 over pi. That would work for the next one. Okay? So, these are not linear, so don't even mess with those. No, this one's linear. You could do that one. I'm not going to do it. Okay? So, if you have any linear equation in n variables, you're going to have a sequence of n real numbers, and we call them ordered n-tuplets. Okay? We'll get to that word later. Arranged, and they are ordered. This one corresponds to the first variable, this to the second variable, that to the third variable. You know, they are ordered. That matters. Okay? And when you plug them in for the variables, they'll give you a solution that's constant, b, whatever it happens to be. They have to, otherwise it's not. So that's how we define a solution for a linear equation in n variables. So let's do example 2. Now we finally get to do what I let the word slip earlier, but I think you knew what it was. Solve this linear equation. x1 plus 2x2 is equal to 4. Okay? Is that going to have a unique solution? No, it's going to have an infinite number of solutions. So how do we represent an infinite number of solutions? What we do is throw in what we call a parameter. And on this one, this is really pretty easy to do. The easiest thing to solve for here is that first variable. Okay? So let's solve for it. x1 is equal to 4 minus 2x2. Okay? Now, at this point, the easiest thing to represent your parameter is, to be your parameter, is your x2. So let's say let x2 equal, do you want to have a favorite name for a parameter? T. That's what everybody's favorite is pretty much. Equal t. Then x1 is equal to 4 minus 2t. So here now is your ordered pair that represents every solution to that original that original linear equation. I'm also teaching differential equations. That's why I'm getting my words messed up. The ordered pair would be 4 minus 2t, comma t. Give me a t, any t in the world. Pick a t. One, okay? So 2, 1. Okay, if you let t equal 1, 4 minus 2 is 2, 1. 2, 1, does that work? 2 plus 2 times 1, 2 plus 2 is 4. High level math today, right? Good. Okay. All right. I like even better, easier, 0. Okay, pick t equals 0, you get 4, 0. And certainly that works. Okay? Any t you happen to choose. You know, 4,574,000. Yeah, I don't want to do that, but you can do it. That would give you another ordered pair that satisfies that equation every time. So that's why we solve for one variable and then pick your parameter t, to the easiest thing you can solve for, and then plug back into the other variables. Okay? Now, is it unique? No. To parametrically represent a solution set, you could have chosen x1 to be the free variable. In other words, solve for x2, and that would have been 2x2 is equal to 4 minus x1. So then x2 would equal to 2 minus 1/2 x1. Just a little bit messier, but then the t let x1 equal t, or t equal x1, it doesn't matter which way you say it, then x2 would be 2 minus t over 2, okay? So then your ordered pair would be t 2 minus t over 2, okay? They don't look the same, do they? But you can find a t, like when, if you let t in this one be 2, then your ordered pair would be 0, 2. In this one, let t equal 0, and you get 0, 2. Same thing, okay? You pick different t's. Here your t was 0, okay? But you can find a t that will give you identically the same ordered pair. And you can't find the t that will give you anything that couldn't be produced by the other one. So it doesn't matter how you express them. There's an infinite way to express those ordered pairs, but once you do, they should produce the same set of ordered pairs, numbers. All right. Actually, I probably should have made one of those a t and one an s, so they're not the same variables. Okay, let's do almost the same thing with in example 3. Only this time we have a linear equation, 3x plus 2y minus z. That's the second time today I've been meaning to write a minus and wrote a equal sign instead. I don't know what's wrong. Minus z is equal to 3. Okay. You can solve for one of these. Which is the easiest one to solve for? You say z? Z is equal to 3x plus 2y minus 3, right? So there's no simple way to get rid of the x's and y. So in this case, you have a 2-parameter system, okay? Earlier, you just had a 1-parameter system. This would be 2. Let's let which one? Pick a parameter. Second? U and v, okay. Let u, or let's say let x equal u and y equal v. So then z would be equal to 3u plus 2v minus 3. So goodness, my writing's so bad I could hardly read that. Okay. So then your ordered triplet, because you have 3 variables, would be u, v, 3u plus 2v. Plus 2v minus 3. Okay, there's your ordered triplet. Again, I'm having trouble reading my writing. Okay? That's one way to do it, not the only way. why in the world did they choose to solve for x? Certainly can, but it made your parametric equations a lot messier. Okay? But they did it this way and had x equal 1 minus 2/3 s plus 1/3 t. 1 minus 2/3 s plus 1/3 t. Y is equal to s and z is equal to t. Okay? So their ordered triplet was this one, 1 minus 2/3 s plus 1/3 t, y, no, st, sorry. Goodness gracious. S comma t. All right. Wait a minute. I shouldn't have this parentheses here. Okay, sorry about that. Okay. And this is the number 3. I can't believe how ugly my writing is today. Sorry. That sneezing I did has just really messed up my head. I hate to do that in class, but I was having trouble breathing. All right. Can these be reconciled? Well, let's just say, in this one, if s is equal to 0 and t is equal to 0, obviously this one, x is equal to 1. So let's do that. Let's let x equal 1, or u equal 1, v equal 0. Then this will be 3 plus 0 minus 3 is 0. And sure enough, that's what we got before. So yeah, even though they don't look like it, these are equivalent parameterizations. And very good choice of not having the same letters for both sets of parameters. Okay. All right. Now, we'll come back to those kind of concepts a little bit later. Most of the time we don't have one equation in 2 or 3 or 17 variables. That's just not very meaningful. But we'll have systems of linear equations. And what we'll be doing is reducing those systems, and if at the end you come down to something that's irreducible, then you introduce the parameters. Okay, and you're probably used to doing that. So let's give a few definitions of what we mean by systems of linear equations. Okay? A system of m linear equations in n variables is a system of, obviously, m equations, each of which is linear in the same n variables. So here's how we usually represent this, and this is really heading in one direction. A sub 1, 1, x1 plus a sub 1, 2, x2 plus a sub 1, 3, x3 plus dot, dot, dot plus a sub n, x sub n. Had to pause and remind myself how many equations, how many variables. It's m equations, n variables. So you have to have n of those. Oh, I left off the subscript. Well, I'll just put it in. 1n. Because all those in the first row, the A's have the first, you got a 2 subscript system. The first subscript says which equation you are, first equation. Second subscript says with which variable are you associated. X1 says A11, A12, X2, and so on. So this is A1n, Xn, and this is equal to Bn. Okay? Oh, I'm sorry. Wrong. B1. Okay. B sub 1. And then we have A sub 1, 2, 1, X1 plus A sub 2, 2, X2 plus A sub 2, 3, X3 plus dot, 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 plus dot, 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 no. Sorry, wait a minute. Stomach's aching. A sub 2n, X sub n is equal to B2. The next one would be A sub 3, 1, X sub 1 plus A sub 3, 2, X sub 2 plus A sub 3, 3, X sub 3 plus dot, dot, dot plus A sub 3 n X sub n is equal to B3. And then we'll continue dot, dot, dot down here, dot, dot, dot down there, dot, dot, dot here, dot, dot, dot here, dot, dot everywhere, dot, dot is equal to dot, dot, dot. And finally, you get your last one, A sub M1 X sub 1 plus A sub M2, I can't write. That first one's an M, the second one's a 2. That came out really ugly. X sub 2 plus A sub M3, X sub 3. I'm writing faster than I'm thinking. The X is regular script and the 3 is subscript, okay? Plus dot, 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 plus A sub M n X sub n is equal to B sub n. Okay. B sub m, sorry. B sub m. Can't get my pen to do well. Okay. These are so tedious to write. Get the subscripts right. Here's the easy way to remember though. The first number, okay, the coefficients have the double subscript and the variables have a single, and the constants at the end have a single. Okay? The double subscript of the first subscript represents the row number, the equation number, 1, 2, 3, 4, 5 to m. The variables, you always line up your similar variables under similar variables, pluses under pluses, and stuff like this. Equal signs under equal signs. You have to be sure those are lined up well too, and then the constant terms under the constant terms. So then your second variable, the second number in your subscript is the variable number. So this is A11 with X1, A12 with X2, A13 with X3, A sub 3, 3 with X3. Well, that was a poor choice, but yeah. So those two match, okay? The first is the row number. So down here it's AM1, X1, AM2, X2, AM3, X3, on AMN, X sub n equal B sub m because these were your row numbers. Okay. Now, I think you know where we're heading here. Later we'll identify a matrix, which are your coefficients, and then a vector, which are your variables, and then another vector, which is your constants, okay? And then you can represent this as something much easier, not having to write as many things down. And leaving off the plus and minus sign, I mean, it's just really nice. Much more a handier way to write. So, what if you have a system like this? The solution of that kind of system, of this kind of system of linear equations, okay, is a sequence of numbers. This is very similar to what we just wrote. Sequence of numbers, S1, S2, S3, dot, 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 up to and including S sub n. No, wait. Yeah, S sub n. That is a solution to each linear equation in the system. I don't know why I wrote SI rather than IS. Beyond me. That is a solution. I left off where I was. Of every equation. Okay. In the system. Okay. I'll go ahead and tell you one reason I think I am having some problems. I had an 8:30 class, went to 9:45, and then immediately I had to go to the help desk. I was on that until right before this class. I mean, I was 11:40, and so it's just been, I had zero time for lunch. So right now, my blood sugar is really low, and I'm having a hard time almost getting things to make sense. So sorry about that. I've got 30 minutes after this class before my next class, and that class goes from 1:15 until 5:45. So I'm going to run down to my office and cram in as much food as I can in doing that. All right. So that's what we mean by a solution. Let's do a very easy system of equation. Now, you've probably done ones like this almost in your sleep. Not quite. 3x1 plus 2x2 is equal to 3 minus, goodness gracious, minus x1. I got to sneeze again. I'll start all this mess over again. I don't know what's causing that. Plus x2 is equal to 4. Now, back in some earlier algebra class, you've probably had a pretty easy way to solve that. What would you do? Rewrite what?
Rewrite one of the variables in terms of
Okay. What you just described is what they usually call the substitution method. That's exactly what I would have done with this. In fact, I would have said x2 is equal to 4 plus x1. Okay, right? And then plug that into your x2 there. 3x1 plus 2 times 4 plus x1 is equal to 3. Solve for x1, then plug back in and get the other. Okay, and that is the easy way to do it for a 2x2 when you can do an easy substitution like that. Now, just about as easy, but let's just imagine you had coefficients here and here, that neither one of them are multiples of either 3 or 2, say 5 and 7, or anything such as that, then that's a really big mess. Okay, substitution, not a good idea on that. So in a sense, there's a couple of other easy ways to solve this. Let's do it the way you were suggesting, and I think I said it too. It was x2 is equal to 4 plus x1. So that made it 3x1 plus 2 times 4 plus x1 is equal to 3. And that would be 3x1 plus 8 plus 2x1 is equal to 3. That would be 5x1 is equal to negative 5. x1 is equal to negative 1. Well, if you knew that, then x2 was 4 minus 1 is equal to 3. So here's your ordered pair, which is your solution, minus 1, 3. Now that one is a unique solution. No parameter involved, no infinite number of solutions, a unique solution. Because you have two variables with two equations. Now not always will that be the case, but in many of the cases, if you have the same number of equations with the same number of variables, there is a chance you could have a unique solution. You may still have an infinite number of solutions, or you may still have no solution. Okay? In this case, we did have a unique solution. Now let's work this a different way. Okay? I'm going to actually do it two more ways. In this system of equations, let's multiply the second equation by 3. Okay? So the first equation would be 3x1 plus 2x2 is equal to 3. The second equation becomes minus 3x1 plus 3x2 is equal to 12. Okay? Now what happens here? Yes, you add them together and you eliminate the first variable. And what you wind up with is 5x2 is equal to 15 and x2 is equal to 3. Perfect. That's exactly what we got here. x2 is equal to 3. Now we can go back and substitute in either one of these. I'd say the second equation is still my good one. Minus x1 plus 3 is equal to 4. So x1 is equal to minus 1. And sure enough, that's what we got there too. Okay? So there is another way to solve. This one is called, the other was called substitution. This is called elimination by addition. Okay? There is another way to do that one by elimination by addition. And here's what I suggest for that one. Okay? Rather than multiplying the second equation by 3, which eliminates the x1, multiply the second equation by minus 2, and that will eliminate the second one. So let's do that one. That would be 3x1 plus 2x2 is equal to 3. And multiplying by minus 2 gives you 2x1 minus 2x2 is equal to minus 8. Okay? What happens if you add now? You eliminate the x2. Okay? And that gives you 5x1 is equal to negative 5. x1 is equal to negative 1, which is the same thing you got here and here. And plug that into your second equation as the easiest. That would be
minus of minus is plus 1 plus x2 is equal to 4, x2 is equal to 3, which is exactly the same order pair you got before. Now, in a 2x2 equation, sometimes substitution will be the easiest, sometimes it won't. Elimination by addition will always be pretty easy to do. But once you get bigger than 2x2s, 3 equations, 3 unknowns, 4 equations, 4 unknowns, these things, nothing is easy with those techniques. So what we're going to develop is something that works, a systematic way to do big sets, and it's based basically more on elimination by addition, okay? Now, there was another possibility there, and that was graphing. And that's what they suggest doing next, and I really don't like that suggestion, but let's do it. Graph the two lines. 3x minus y is equal to 1. Now, here's a system of equations. Now, I'm going to write the second equation in a different color. You pick a color. You say red? Okay, we'll do red. Okay, the second equation is 2x minus y is equal to 0. All right. All right. Now, I'm so hungry. I haven't pulled out my watch either, so I have no idea how long I've been going. Are we over at past time? What's that? Over. I am so sorry. We'll pick up this one next time. Okay, sorry about that. I was going to say, why am I so hungry? It's because we already gone over. Okay, so let me, somewhere here I have it. We will pick up, go backwards, and do this discovery next time. Okay. Homework exercises here. There's not many that you could do, but let's see at the end. Wow, this is a long section. You can do 1 through 5. I know you can do those. You can do 7 or 9. You can do either of those. And by the way, I don't know if I mentioned this about the book. This book has 2 features. I won't see them here. Okay, I'll just tell them. Calchat.com, one feature. Okay, and I give the odd number of homework exercises for 2 reasons. Number 1, odd number answers are in the back. Second reason, odd number answers are also given at calchat.com. So if you try to do this, check your answers in the back. If you can't see it, if you can't get that answer and don't know how they got that answer, then go to CalcChat and they'll show you the worked out solution. It's a free website. You don't need any code or anything else. Your grandmother could go to this website and look at it. You know, it's perfectly, it's open for everybody. So if you still can't figure it out, come back and ask questions. To do any of the odds 1 through 5, they're all at CalcChat, either 7 or 9. They're in the back of the book and at CalcChat. And then they're going to say graphical analysis. We'll do that next time. Okay, so that's just very few to do that. Oh, not at all. You want the front or the ISBN? Just the front. You don't need the ISBN?
No, I just need to see what kind of, because usually I get ebooks.
Okay, yeah.
I mean, I like real books, but
Yeah.
it's just easy. So
Yeah.
I don't have to keep up with something.
Exactly.
Well, when I
One computer is less than many books. Right? Got it. Yeah.
I see.
All right.